Now let's think about our unit vectors of R3 that we use, our standard ones, our I hat, our j hat, and our k hat. Now let's think of these in terms of cross products. We have our I hat cross j hat, which if we go through the whole process, we'd figure out to be k hat. Then we have our j hat cross our k hat is equal to our I hat, and our k hat cross our I hat would be equal to our j hat. That seems good enough for right now, and that should make sense, and you could calculate these. So what would be j hat cross I hat? And you might think, oh, well, k hat. But let's actually do this calculation to see if this is true. We have our I hat, j hat, k hat, determinant of, and then j hat, 0, 1, 0, and then I hat, 1, 0, 0. So we have I hat of 1, 0, 0, 0 minus j hat of 0, 0, 1, 0, and then plus k hat of 0, 1, 1, 0. Well, this determinant is equal to 0, so we get 0 I hat minus, well, 0 j hat, and then minus 1 k hat. So this is the vector 0, 0, negative 1, or, in other words, minus k hat. So j cross I is not equal to k. It's in fact negative k. And in fact, when you flip all of these, so k hat cross j hat, that's going to be negative I hat. K hat, I hat cross k hat would be equal to negative j hat. The cross product is not going to be commutative. And how this works, you can think of it as a cyclic property. You have an I, j, and a k here, and it moves around in a circle. So I hat cross j hat equals k hat. J hat cross k hat equals I hat. But if you go against the circle, I hat cross k hat, since you're going against it, it'll be negative j hat. So again, this establishes that the cross product is not commutative. And in fact, it's not even associative. If we do I cross j hat, well, we know these are parallel, so these should equal 0. So you have 0 cross j hat, which is just 0. But if you did this first with I cross j, well, we know I cross j is equal to k hat, and then I cross k hat is equal to negative j hat. So in fact, these are not equal. So associativity also fails. So that begs the question, what properties are true? And this is why it's important to start looking at these properties, asking what is true, what isn't. Because the ones that you may have learned from grade school, associativity, commutativity, all these different things, they may not always hold when you get into higher mathematics. So what properties do hold? Well, in fact, as you may have guessed, A cross B, although it's not commutative, it is equal to negative B cross A. Luckily, our scalars we can distribute nicely. So C times the vector A cross B is the same as C times the vector A cross the vector B, and it's equal to A cross the vector C times the vector B. Now, we have a sort of distributive property as well, where A cross the vector B plus the vector C is equal to A cross B plus A cross C. And also on the other side, A plus B would cross C is equal to A cross C plus B cross C. And using our dot product and our cross product, we kind of have something where we can move our parentheses. If we have A dot cross C, that's going to be equal to A cross B dot C. A cross B cross C is going to have to be A dot C times the vector B minus A dot B times the vector C. Because remember, this dot product is a scalar, so that's why we just have this regular multiplication there.